In my last video, we introduced the concept of the imaginary unit I. In this video, we're going to use that concept to build what we call the set of complex numbers. And so we say, by definition, a complex number written in standard form is any number a plus bi, where the a and b parts here, these are actually the real number parts. What you'll see here is this I part is actually the imaginary part of this number. So we say the number a is the real part of this number, and then the number b is the imaginary part, where we have some number a plus bi. And so let's label this here. We'd say a. This is our real part of the number. And we'd say that bi is the imaginary part of the number. Now, this is not to say that the value of b is not real. It's just that it has an imaginary unit glued to it, so we call that the imaginary part of this number. But the thing is, we refer to any number where we have a real part plus an imaginary part, which do not combine. They don't combine. No like terms here. They form what we refer to as a complex number. So this set of complex numbers that you see over here, we say these are all the numbers of the form a plus bi. Basically, what I want to point out is all real numbers are in this set of green right here. And what I'll notice is when I write this as a complex number in standard form, this would be some number a plus no imaginaries. So basically, if you add on no imaginary parts to a number, you get something that we refer to as a purely real number. Whereas if we were to say, well, all of these numbers over here, these are considered to be imaginary numbers. And when you put these with a real number, you get what we say is the set of complex numbers. So an imaginary number, a plus bi, would be any number here where we have a real part plus an imaginary part. That whole thing makes an imaginary number. And then you see we have this certain subset of imaginary numbers that we refer to as the purely real numbers. And these would be numbers of the form 0 reals plus just an imaginary part. But in our complex number, basically we would say the a part is equal to 0 and the b part specifically does not equal 0. So these are things like negative 4i and just 6i, because they have no real part that is not 0. We refer to those as not just imaginary, but purely imaginary. But basically what we're going to say is when you take a real and you glue it onto an imaginary, you get what we call a complex number. And when you write it this way, we say it is a complex number written in standard form of a complex number. So because we have this set of complex numbers here, again, I want to go through these really quick definitions of what we mean by imaginary numbers in the first place versus purely imaginary numbers, and then purely real numbers. So we say for any number, real number plus imaginary number part, a plus bi in standard form of a complex, we say if the b part here is not equal to 0, that is to say there is an imaginary part, then we say that the number a plus bi is an imaginary number. So basically any number that actually has an imaginary part to it, we call it an imaginary number. Whether that's 2 plus 3i or 0 plus 3i, it's got an imaginary, so it's imaginary. So what sets the purely imaginary numbers apart from the imaginary numbers, that's these down here, is that a is equal to 0, or that is, we say the real part is 0. There's no real part to it, it's just an imaginary part. So the b part can't be 0. We say the number a plus bi is what we call a purely imaginary number. And on the same note, if we have some a plus bi where we say the first part is not 0, okay, so there is a real number part to it. It's just that the second part is specifically equal to 0. So these are numbers like 2, 3, 4. 4 plus 0i, basically. Then we say this number is purely real. So the only thing I want to kind of mention here in this video, besides the fact that complex numbers in standard form are written in a plus bi form and have both a real and imaginary parts, maybe, we say that two complex numbers and their equality we want to comment on in this video. So we say if I had a number a plus bi, and we say a different complex number in standard form, c plus di, we say that these are equal if and only if a is equal to c and b is equal to d. And this is really kind of a fancy way of saying, well, hey, a and c are the real parts. So if these two numbers are equal, well, then the real parts, they sort of have to be equal. And likewise, if these are equal, then b would have to be equal to d, because these could only be equal if they're the same number, and those are the imaginary parts. So b would be equal to d and a would be equal to c. So using this property, what we want to do is find values of x and y in this example that satisfy these equations. Well, what I notice here is I have this 5x minus 20i. This is kind of like our a part, and this is our bi part. And over here we say 35 plus yi, well, that's what it's equal to. We say this is like our c part, and this is like our di part. So what we could conclude is this, well, the 5x, whatever that is, has to be equal to 35. And so solving this, well, the first thing I'm going to do is equate them. And I say, well, whatever the 5x is, it's got to be equal to 35 if these two complex numbers are equal. So dividing both sides here by 5, we end up with x is equal to 7. And then furthermore, we would say, well, then the negative 20i, negative 20i's, that would have to be equal to the yi part. And so it just basically, we could come up with the conclusion, well, then negative 20 is equal to y. So negative 20 is equal to y, and there's really no solving we need to do here. And we could certainly go back and check this by plugging these in. If I were to plug in a 7 for my x here, I would get this. I would get 5 times 7 minus 20i as our left number here. And on the right side, plugging in negative 20 for y, we would get 35 plus a negative 20 times I. And you can see that this negative 20 and that negative 20 are equivalent. And you can see that this 5 times 7 and this 35 are certainly equivalent. So trying this again, I would encourage you to pause and try this on your own. But going forward, we would say this 9 part, the real part here would be equal to this real part here. That is, 9 would have to be equal to negative 2x. And furthermore, the 4yi has to be equal to 3i. In other words, we could say that the 4y part is equal to 3. So it follows that in this case, x is equal to negative 9 halves. And over here, if we divide both sides by 4, we get y is equal to a positive 3/4. And those would be those parts of those two complex numbers. Cheers.